This talk is about the group isomorphism problem. The group isomorphism problem is to determine whether two groups given by their Kelly tables are isomorphic or not. That is, if there is a bijection between the elements of the two groups such that the group operation is preserved by the bijection. The first algorithm, attributed to Tarjan and documented in a paper by Miller in 1978, has a quasi-polynomial running time. I mean n to the power of log n time, where n is the order of the two groups. After almost half a century, the current best-known algorithm still has a quasi-polynomial running time. Only the constant factor in the exponent is improved to 1/4. The major open question on this front is if one can get an algorithm with sub-quasi-polynomial time. In other words, n to the little of log n time. When discussing group isomorphism, it is inevitable to talk about its sibling, graph isomorphism, which is to determine if two unlabeled graphs are the same or not. In some sense, the two problems are similar. They both are extensively studied since the 1970s, and until now, the complexity of the two problems are unsettled. Both are neither known to be in P nor to be NP complete. Interestingly, the best known algorithms for both problems have quasi-polynomial running time. On the other hand, the two problems also have significant differences. For group isomorphism, it naturally has a quasi-polynomial time algorithm, while the trivial solution for graph isomorphism takes exponential time. The progress of the two problems are also different. The improvement on group isomorphism was slow, while for graph isomorphism, moderately sub-exponential time algorithms were obtained in the 1980s, and recently, the upper bound was improved to quasi-polynomial time. Furthermore, the reduction between the two problems are also different. Group isomorphism is polynomial time reducible to graph isomorphism, but it is unknown if graph isomorphism is reducible to group isomorphism. In order to further improve the upper bound for graph isomorphism, to get a sub-quasi-polynomial time algorithm, it is necessary to first get a sub-quasi-polynomial time algorithm for group isomorphism due to the reduction here. So, group isomorphism becomes a bottleneck for graph isomorphism. Group isomorphism is also an interesting problem in math. In a blog by Richard Lipton suggesting group isomorphism as a polymath problem, Tim Gowers proposed a method for the group isomorphism problem. But the proposed approach still has a quasi-polynomial running time in the worst case. In this work, we study group isomorphism for a special class of groups, P groups of class 2 and the exponent P. A group is a P group of class 2 and the exponent P for some prime number P if the following two conditions hold. First, all the elements in the group, except the identity, have order P. Second, every element in its commutator subgroup is commutative with every element of the entire group. P groups of class 2 and the exponent P have long been identified as the most difficult case for group isomorphism. The structure of this group class is much simpler than general group, and pretty much well understood. However, with these structural properties, the running time for this class is n to a power of 1/6 of log n. No significant improvement compared with general group isomorphism. More importantly, all the known techniques for group isomorphism do not work well on this special class, including Gowers' proposed method. As our main result, we give an algorithm for P groups of class 2 and exponent P with running time n to a power of log n to 5/6. Our result makes use of a structural property for P groups of class 2 and exponent P, called Bayes correspondence. Bayes correspondence shows that every P group of class 2 and exponent P corresponds to a linear space of matrices over the finite field Fp. In this linear space, every matrix is a skew-symmetric matrix. The matrix transpose equals its negative. Furthermore, let M be the number of rows or columns of each matrix in the space, and R be the dimension of the linear space. M plus R is upper bounded by log n to the base P. Bayes correspondence implies that two P groups of class 2 and exponent P are isomorphic if and only if their skew-symmetric matrix spaces are isometric, meaning that there exists a square matrix Q such that the conjugation of one space by Q equals another. The conjugation of a space by Q is obtained by multiplying Q and Q transpose from the left and right to each matrix in the space, and taking the union of the resulting matrices. With the matrix space representation in mind, the difficulty for the isomorphism testing of P groups of class 2 and exponent P is to determine the correspondence between the skew-symmetric matrices of the linear spaces obtained from the two groups. If the correspondence between the matrices is known, then the problem reduces to the matrix tuple isometry problem, which can be solved in polynomial time, obtained by Evanus and Qiao. If one determines the correspondence between two matrix spaces by trying all the possible correspondences, because there are P to the R squared possibilities, the result is a quasi-polynomial time algorithm when R is linear in log n. No improvement compared with the current best algorithm. Hence, in order to get a sub-quasi-polynomial time algorithm, one needs to avoid enumerate all the possible correspondences. As our main technical contribution, we show that there is an algorithm to determine whether two skew-symmetric matrix spaces are isometric in time P to the power of M plus R to 1.8 times log P. The overall algorithm is obtained by combining Tarjan's algorithm for large P. Our result is obtained by combining three new ideas together. First, we develop a novel individualization and refinement method for matrix spaces. Second, we characterize matrix spaces that only contains low-rank matrices. Finally, we combine the first two ideas together to reduce the matrix space isometry problem to the matrix tuple isometry problem. Let me start by the first ingredient, the individualization and refinement for matrix spaces. The individualization and refinement method is a classic and powerful technique for graph isomorphism. Take the Peterson graph as an example. The graph at the beginning is highly regular. All the vertices look the same and all the edges look the same. To break this regularity, it is critical to bring in some irregularity. Individualization introduces irregularity by carefully selecting a subset of vertices and assign each of them a distinct color. In this example, we choose three vertices colored by red, purple, and green. Then, the refinement expands this irregularity in a manner of preserving the isomorphism as the other vertices start to look different. Each not individualized vertex takes the vertex color of its neighbors as the label for itself, and then assign colors so that vertices with the same label have the same color. This process continues until no more new colors can be created. If we are lucky enough, say by individualizing a small set of vertices, the color for every vertex is different after the refinement. We can use the refinement to test isomorphism. More formally, For a graph with n vertices, if individualizing t vertices can distinguish all the vertices, we can test the isomorphism in time n to the t by enumerating all the possible images of the individualized vertices and check if the correspondence between individualizations extends to an isomorphism. Because the individualization and refinement approach is a very powerful tool for graph isomorphism, and because the natural connection between group isomorphism and the graph isomorphism, people wonder if it is possible to generalize individualization and refinement for the group isomorphism problem. In this work, we devise an individualization and refinement method for matrix spaces, and use the aforementioned Bayes correspondence to speed up isomorphism for P groups of class 2 and exponent P, based on this new approach. The goal of this new method is to distinguish matrices in a matrix space so that we can establish a correspondence between matrices from different matrix spaces. In our approach, for a matrix space, the individualization selects two matrices, a left matrix L and a right matrix R. In the refinement step, for each matrix in the matrix space, we multiply L and R from the left and the right, and take the resulting multiplication as the label for the matrix from the space. We say two matrices are distinguished if their labels are different. Ideally, we want to give matrices in a matrix space distinct labels, so that all the matrices are distinguished. If this is possible, we can establish the correspondence between two asymmetric spaces as follows. Suppose the individualization matrices for one space can give different labels to all the matrices. If we use equivalent individualization matrices for another space, up to an asymmetry between the two spaces, matrices in the other space are also distinguished, and the set of labels produced for the two spaces are the same. So, we can construct a bijection between the matrices of the two spaces by mapping matrices with the same label together. And then, the problem reduces to the aforementioned matrix tuple asymmetry problem, which can be solved efficiently. What's the cost of this individualization and refinement method? The key is to find left and right matrices for both spaces that are equivalent up to an asymmetry between the two spaces. To achieve this goal, once we determine individualization matrices for one space, we need to enumerate the equivalent ones for another space, because the asymmetry is unknown. Since the possible left and right matrices for another space can be arbitrary, we need to try all the possibilities, which have exponentially many in terms of the size of individualization matrices. So, it is desirable to minimize the size of the individualization matrices to minimize the cost of this approach. We show that if the rank of every matrix in a matrix space is at least k, then max of R over square root k and square root k rows are sufficient for the left individualization matrix, and the same number of columns is sufficient for the right individualization matrix. Roughly speaking, the individualization is efficient only if all the matrices in the matrix space have a high rank. However, in general, for a matrix space, it is possible that some matrices have high rank and some others have low rank. In this case, distinguishing all the matrices is too expensive, as the individualization matrices need to be large. To get some intuition for the next step, let's have a look at what happens if individualization and refinement only distinguish part of the matrices. After applying some small individualization matrices, some matrices have zero matrix labels, These matrices are all of low rank and form a linear subspace of the original space. If applying such individualization and refinement to two asymmetric matrix spaces, we can only establish a partial correspondence between the two spaces. I mean, if two matrices from different linear spaces have the same label, like A and B here, their difference is a low-rank matrix with respect to an asymmetry. The main question is then how to handle the linear subspace in which all the matrices are of low rank. Our answer is a characterization of low-rank matrix space. Suppose every matrix in a linear space is of rank at most k. We show that there are invertible matrices S and T, such that if we multiply S and T from the left and right to each matrix simultaneously, the resulted matrices only have non-zero entries in the last k-square rows or columns. In other words, the induced submatrices on the first m minus k-square rows and columns are all zero matrices. We remark that two previous works give similar characterizations, but only hold for a large field. The number of elements in the underlying field needs to be larger than k, the rank upper bound of the space. Our result works for arbitrary fields. To this end, we are able to handle matrix space all of high-rank matrices. We can also handle matrix space all of low-rank matrices. But for general space that contain both high-rank matrices and low-rank matrices, we still don't have a solution yet. To resolve this problem, let's first combine the two techniques given so far together to make the matrix space more organized. More specifically, we first apply the individualization and refinement and choose a linear basis of the matrix space according to the lexical order of the labels as a representation of the entire linear space. At the end, we apply low-rank characterization to all the matrices in the basis. Here is a figure illustrating the result. The first few orange matrices have zero labels, and they span a low-rank matrix subspace so that only the last few rows or columns have non-zero entries. The following blue matrices have non-zero labels given by individualization and refinement, and the order of those matrices is determined by their labels. The linear basis is not unique, but for matrices at the same position in different bases, their difference is a matrix from the orange matrix subspace. Now, we give our final reduction to the matrix tuple asymmetry problem. Here, it is helpful to think the skew-symmetric matrix space as a three-dimensional tensor by taking an arbitrary basis of the skew-symmetric matrix space. When we look at the tensor from three different directions, we get three matrix spaces. One is the original skew-symmetric matrix space, and two others are matrix spaces of R by M matrices. Our idea is to apply the matrix space individualization and refinement method and the low-rank matrix characterization to all the three matrix spaces. This is a visualization of the resulted structure. The transparent region contains only zero entries. The blue region is non-zero but fixed no matter which linear basis we use for the three directions. The orange region, which contains three sides, varies when we use different linear bases on the three directions. A nice observation here is that the transparent region and the blue region together take most part of the tensor. This means that most of the tensor is fixed after applying individualization refinement and low-rank space characterization. In addition, To determine if two groups are isomorphic, we only need to determine if the orange region for the two linear spaces are the same up to the change of basis from the three directions. To get our final reduction, we first further decompose the orange region into three matrix tuples for the three different sides. Because the orange region contains a small fraction of all the elements in the tensor, so we can afford to fix the matrices in the orange region by enumeration. Second, we flip two sides of the orange region so that the three matrix tuples from three different sides are on the same plane. At the end, we use a few new matrices to encode these three matrix tuples. To make sure the matrix tuples from different sides do not intervene each other, we encode matrices from different sides in different matrices in the new matrix tuple. We show that the newly constructed matrix tuples are asymmetric if and only if the original skew-symmetric matrix spaces are asymmetric. To summarize, we give an algorithm to test the isomorphism of P groups of class 2 and exponent P in time n to the power of log n to the 5/6. Our result is obtained by combining a novel individualization and refinement method for matrix space, a low-rank matrix space characterization, and a reduction to the matrix tuple asymmetry problem. There are a few open questions. Is there an even faster algorithm for this group class? We believe the current bound is not optimal. A more ambitious goal is to extend the current result to a faster algorithm for general group isomorphism. Our results remove the major barrier, but there might be several other intermediate steps towards this goal. For example, for solvable groups, a generalization of P groups of class 2 and exponent P, it is unknown how to test isomorphism in time better than quasi-polynomial time.